Hello, everyone. Um, Welcome to Scalable Algebra course, section 4.3. We're going to go over logarithmic functions. So, first, as a motivation example, I would like to start with finding the inverse of 2 to the x. So, why do we need logarithmic functions? So, logarithmic functions are the inverse functions of the exponential functions. So, they're used heavily in multiple areas. And in this section, we're going to go over the basics about that. So let's graph 2 to the x as a start. So let me create a table. Here's my x values and here's my um, y values. Let's choose like simple negative 1, 0, 1, 2, and y is 2 to the x. So I get 2 to the negative 1, which is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. And then 2 squared is 4. So this is from exponential functions. So we just kind of like plot those points at negative 1. It's 1 over 2, 0, 1, and then 1 comma 2, and then at 2 it's 4. So the graph kind of like a graph that grows really fast on towards right and then getting close to the x-axis on the left. So inverse functions, you will know, is just kind of created by, of course, the function needs to be one-to-one, and this is a one-to-one function. If you draw horizontal lines, it intersects once with the graph. So the inverse function, to find the graph of the inverse function, you need to swap the variables. So I have x and y again, but this time I'm going to swap the values. So at 1 over 2, y value will be negative 1. That's what I got from the first row. At 1, its y value will be 0. 2, it's going to be 1. And at 4, it's going to be 2. So we just interchange the variables to get the inverse function, the graph of the inverse function. So we call this inverse function the logarithmic function base 2. So at 1 over 2, it is negative 1. At 1, it's 0. At 2, it's 1. And at 4, it's 2. As you see, the kind of like that black dark blue graph is kind of like the mirror image of y equals mirror image of 2 to the x when y equals x is like our mirror. Um, that's the inverse function of 2 to the x, and we just denote it by f inverse of x log base 2. That's the name of the function, and my input will be simply x. That's the inverse function of 2 to the x. So we're going to be using that one for especially working with the exponential functions and equations regarding that, regarding exponentials, when you have the unknown variable at the exponent. So next we define it. So as you see, when I have log base a of x equals to k, this is true when x equals a to the k. If you see here, x is my input, and I just put it at the bottom here. A is what I called base, like the exponential case, and it shouldn't be 1. It's greater than 0, because if it's 1, you just get powers of 1, which is itself. So a is greater than 0, and k is a real number. And here, when you have y equals log a of x, that means here input is x and output is y. In the exponential format, it becomes x equals a to the y. So you see y becomes an input and x becomes an output. So um, it's kind of like we just say usually the logarithms compute to exponents. That's the reason. It's kind of like that that exponent value becomes my output when I convert an exponential equation into a logarithmic equation. So they represent the same information, by the way. It's kind of like inverse function applied to both sides. I'm going to show that to you more on the examples. Look at this first set. So if I have 3 squared equals 9, here, let me just do this in detail. Like base, as you see, base is base is 3, and this one, base is 3. Base value is, let me just base um, base is equal to 3. Exponent is 2, and that exponent will be my output. So if you want to write it in a log form, what I'm going to say is log base 3 of 9 equals to 2. As you see here, output of log is the exponent. So we just say log computes the exponent most of the time. So that kind of like solve this problem. Which power of 3 is 9? So that's what you're looking at. Which power of 3 is 9? That's what's solving. For example, here 4 to the negative 3 is 1 over 64. Base is 4. So I'm going to have log base 4 of 1 over 64. Which power of 4 is 1 over 64? That's going to be negative third, negative 3. And here base is a. I just write the most general form. Log base a of z, which is the output of the exponential expression, is just equal to the exponent b. So that's like how you convert them. These three, like these equations are represents the same information. So we have some common like good notation in here. If you have base 10, you don't write the subscript and you just write log. That means my base is 10. If the base is e, we call it natural logarithm. It's going to be written by ln. Especially on the calculators, you can just see those two buttons in there. And some properties in here. You see, I here put some graphs over here, but this is log base 2 of x. This is ln x. They kind of like look similar, but of course, like it like at 1 0, they're both passing through 1 0, but at like different points, they may have different values, but they really look similar. There are a couple of things. If you look at the domain of this blue graph, it's just on the right side of y-axis, so the domain will be let me just see, domain will be 0, infinity. And if you look at the range, it covers the whole y-axis. Think of this right side of the graph going up and left side going down, so it covers the whole y-axis, so the range will be negative infinity, infinity. And this is, as you see, this one is the domain of the exponential function, and this the range of the exponential function. So it's just they're swapped because we're looking at the inverse of the exponential function. So without using a calculator, it's not really hard to do them. It's kind of like I told you this in the previous page. This really computes the power of 3 that gives you 81. So you can, in an easy way, you can set this equal to 0 and convert it into exponential. So 3 to the x equals to 81, but 81 is simply 3 to the 4, so that means x needs to be 4. All right, so x needs to be 4. Or look at the second one. Which power of 4 is 1 over 64? That's going to be 1 over 4 to the 3, and that's 4 to the power negative 3. So that means x needs to be here. The exponents must be matching, so x must be negative 3. So negative third power of 4 gives you 1 over 64. Here, no subscript, so that means my base is 10. It's the common logarithm. We spoke about that in the top of the page. You see that top of the page, spatial logarithms, common log, base 10. So you're trying to compute this one. Which power of 10 gives you 1000? So you can see that's going to be clearly x will be 3, the third power. As you see, the logarithms compute the exponent at the exponential version of it. That's why we all the time say log computes the exponent. Look at this one, same way. This is x, and 10 to the power x equals 0.01. But 0.01 is 10 to the negative 2. So from here you can just see x must be negative 2. So 10 to the negative 2, negative 2 power of 10 gives you 0.01. The last one is with the ln. Here bases, as you see, base is e. When you see ln, natural logarithm, base is e. So here you're asking this question, if this is equal to x, I try to compute this. Which power of e gives you square root of e? So in these problems, when there's no calculator, most likely, I mean, you will be able to write that write the expression inside ln or log as a power of the base. So square root of e, you can just see I can write it as e to the power 1 over 2. So that means x must be 1 over 2. So you see that just computes the power of e that gives you square root of e. So I hope it's clear so far. Now we go into the next part. If you, of course, there's some nice properties, really nice properties. Log base a of 1 is 0 because a to the 0 is 1. Any power of a when a is not any power of a when a is not 0, it's just 0 power gives you 1. So that means log base a of 1 will be 0, and you will get log base a of a if you insert the base number to the log. That's going to give you 1 because a to the 1 is a. Which power of a is itself is the first power. Here's a nice property. These 3 and 4 are really important properties in solving equations. Log base a and a to the x, since they're inverses of each other, they kind of like isolate each other and you get just x. In the same way, if you have a log base a of x, a and log a, they isolate each other and you get x. So we're going to see that in these examples. Look at the first one. This is basis 10 here. Don't forget basis 10. So log and base 10, these two isolate each other by property 3, you get 0.4. Or for example here, log, here's 10, you need to write it as a power of 10. I got log 10 to the power 1 over 2. As you see, these two will isolate each other. Kind of like, I don't want to directly say cancel, but they isolate. They just kind of like applying inverse, like multiplying by 2 and then dividing by 2, like adding 3, subtracting 3. So they cancel and you just get 1 over 2. Or this one, ln cube root of e, again, right, this is a power of e, so it's going to be ln e to the power 1 over 3. I hope it's clear. Look, this ln and e, they isolate each other. And your final answer will be here, 1 over 3. Here, as you see, it's directly written in that form. 5 log 5, they're kind of like you compose them. They cancel each other and you get x squared plus 2. They isolate each other. Like here, e and ln, they isolate each other and you simply get z squared. So the next one, graphing log base 4 of x. You can really use 4 to the x to graph this. Or you can directly just compute the values. I mean, it's all fine, but use powers of 4. That will be really helpful. Base is 4. So base is 4. Here, let me use this one. That one was green. And yeah. So here base is 4. So use powers of 4 for your x. Like xy, or the other way is you can graph 4 to the x and flip the variables, and then you can get the graph for log base 4 of x. Like powers of 4, you can use 1. You cannot use negative values. Just keep that in mind. It should be positive because you're kind of like here. It's computing. The output is simply in the log case is the exponent. So it's kind of like whatever you insert in here, that's going to be a power of 4. So that means it can't be 0 or negative. It should be positive. So if you plug in 1, log base 4 of 1 will be 0. If you plug in 4, log base 4 of 4 will be 1. Right? So at 1 it's 0. At 1 it's 0. And at 4 it's 1. That should be good, but also you can maybe check like 1 over 4, and log base 4 of 1 over 4 will give you negative 1, because which power of 4 is 1 over 4? It's negative 1. So at 1 over 4, its value is negative 1. So as you see, it looks like a similar graph as log base 2 of x. But going down in here, just keep in here vertical asymptote is the y-axis, and it should be on the right side. Its domain is the positive values. So you can check with your calculator, really, like log base 3 of negative 7 or log base a of 0. these are all like does not exist, because like whatever you plug it in there, it should be positive by the definition, guys. Because remember, that input that you plug in the log is an exponential expression. So that's why it's positive. And the range of exponential expressions are positive, so that means once you invert it, the inverse will have the domain positive value. So that's why that's like another kind of like way to express this. So for example here, finding the domain of this function, whatever you plugged in the log must be positive. So I have 3x minus 2, that should be positive, greater than 0. So I solve this inequality. Add 2, add 2 to both sides. 3x is greater than 2. Then divide both sides by 3. So I got x must be greater than 2/3. So it should be greater than 2/3. If you plug in, for example, 0, it's not going to work. If you plug in 2/3, even that will not work, because that will make it 0. Log of 0 is not defined. So we get the domain to be 2/3, comma infinity. That's what we have. So now we get into the next part, in which we're going to be solving some equations. Solving equations are not like, it's pretty straightforward, but here the point is this: you should understand like what you need to apply to cancel or isolate that function. For example, I have 10 to the x equals 0.0001. So to both sides, if you want to get rid of exponential expression, the base, then you need to apply log. If you have a log and cancel that, then you need to apply exponential. So like exponentiation with a base given in the problem. So in this case, I'm going to apply log to both sides. So these two will isolate each other, and I'm going to get x equals log of 0.0001. This is the exact value, by the way, and you can find that it's going to be, if you use a calculator, you will see that it's like -4. So I can show this to you on my calculator. If you look at log button is here, and I'm going to be plugging in 0.0001 close parentheses and hit enter. That's going to give me -4. So that's what we have. So now let's take a look at the other one. It's just similar idea. Again, we apply log to both sides to get rid of, I mean, of course, like this 2. I want to just apply that right here. But if you apply log, it's going to be log 10 to the x equals log 45. And these two will cancel, isolate each other. So x equals log 45. This is the exact answer. And then if you plug this in the calculator, use again that log button, log of 45, I get 1.653. So it's going to be 1.653. It's the one. And then here you're going to be applying ln. So e to the x equals 5. So apply ln to both sides. These two will cancel. I got x equals ln 5. And let's find ln 5 over here. If I look at ln 5, close parentheses, I get 1.609. So it's going to be 1.609. So this is when you have the base given, like exponential expression given, and you want to cancel that base and get the exponent by itself. So if you have log now, you're going to now exponentiate. So here base is 10, so exponentiate both sides by using base 10. So 10 and log will cancel, isolate each other. So we got x equals 10 to the 3, which is 1,000. Or here, it's a log, same again. Again, I apply base 10 to both sides. So x will be 10 to the power 1.4. Let's compute that one. So I'm trying to compute this. 10 to the power 1.4. Use that exponentiation sign, the caret. So 10 to the power 1.4. That gives me 25.119. So it gives me 25.119. Right? The last one is, you see, the base is -2. The base is e. Base is e, so right side is negative 2, so I'm going to apply base e to both sides. These two will cancel. And let's see, sometimes it doesn't work. So x will be e to the power negative 2. So that's e to the power negative 2. Let's compute that one. E to the power negative 2. So you do second ln power negative 2. That gives me 0.135. 0.135. That's what we have. So I hope these are clear. So if you have exponential expression, then you apply log to get rid of the exponential expression and get the exponent by itself. In here, if you want to get rid of the log, then you need to apply the exponentiation to both sides, and that's going to give you the kind of like variable or the expression inside the log. Now, next part, graph the following functions. I mean, it's just really the similar idea that you can follow that we did in there. It's kind of like graphing those points in there, but be careful. This +2 means the graph is like shifted up. This -2 means graph is shifted to the right. So it's kind of like you can use a graphing calculator for this purpose. But if you want to just like graph it by hand, you really need again maybe like use 3 points, powers of 5. So I'm going to get like 1/5, and then I'm going to use 1, and then I'm going to use 5. So it's going to be 2 plus log base 5 of 1/5, which is -1. So that's going to be 1, because this is -1. This part is -1. If you plug in 1, it's going to be 2 plus log base 5 of 1. This is 0, so it's going to be 2. And 2 plus log base 5 of 5, which is 1. So that's going to be 3. So it's kind of like log base 5 of x, graph of that, and then shift it up 2 units. So you can kind of shift it up. So at 1/5, so 1, 2, 3, 4, 5. At 1/5, 1, 2, 3. At 1/5, it's 1 somewhere here. At 1/5, it's 1. At 1, it's 2 here, and then 2, 1, 2, 3, 4, 5. At 5, it's 3. So the graph would look like this. Since that's like shifted up, it's going to be still like going through close to the y-axis. That's what you have. So that's how you graph it, or you can use a graphing calculator as well. Like this is like really similar, but you need to use this time powers of 10. So it's like you can use 1/10, and then 1 and then 10. But of course, like here -3 is involved in there, so you can just like kind of adjust those values in there. Like, what do I mean is this. If you want to get 1, that's going to be simply at 4. So if you plug in 4, then you will get log 1, which is 0. Then you plug in 13. If you plug in 13, that's going to be log 10, which is simply 1. So at 4, it's 0, and at 13, it's 1. It's going to be a little bit like kind of a little bit bigger graph, but let me just, because it's just shifted to the right, and let me just see, shifted to the right. So maybe shifted 3 units to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Maybe here its value is simply 1. Its value is 1 right here, and at 1, 2, 3, 4, its value is 0. So it's kind of like going this direction. but at the same time, since that's shifted to the right, the axis, the y-axis is also shifted to the right. This is the graph x equals 3. As you see, you cannot plug in 3. X must be greater than 3 because you need to plug in positive values. So the graph will look like this, coming close to x equals 3 line, and then going to the right, same way. Can you see that? It's kind of like this x minus 3 means you shift y equals log x 3 to the right. Sorry for the bold writing because I'm writing it a little bit slanted. I hope this is clear. Like, really what you need is powers of 10 in log, but you can use a calculator to get not exact numbers, but like kind of approximations. That will work as well. But yeah, you can use a graphing calculator as well. Like, for example, let's do log x minus 3 over here. So I go in here, let me clear this one. I do log x minus 3 and then close parentheses and then graph that one. You see that's kind of like the graph that it shows over there. It just doesn't show in there, but I want to tell you this. It's kind of like getting close to that line, but never touches, but it goes down. So you can just see that over the graph. I mean, it's easy to graph this on Desmos, or you can use something like a TI-84. That should work as well. So yeah. So let's go into this next example. Again, finding the domain. This time you have a quadratic in there. Like I want here. You need to check the sign in here. 4 minus x squared must be greater than 0. Remember, I said anything in the log or ln must be positive. So you need to solve this inequality. And if you solve the equation, you get two boundary values. Like if you solve 4 minus x squared equals 0, then 4 must be x squared, and then x must be minus plus 2. So you need to check the sign in here. Check the sign. What does that mean? So I'm gonna use the number line. This is negative infinity. This is positive infinity. This is, let's say, negative 2. This is positive 2. You need to check the sign when this is positive or negative. So take a test value. Let's say test value negative 3 here, test value 0 here, test value 3 here. The green are the test values. So we're going to just check these values if they're positive or negative over there. If you plug in negative 3, you see that it's going to be 4 minus negative 3 squared, which is going to be 4 minus 9, and that's going to be negative. If you plug in 0, it's going to be 4 minus 0 squared, which is 4, which is going to be positive. And the last one, 4 minus 3 squared, as you see, 4 minus 9 is going to be negative. So that means this graph is positive only in between negative 2 and 2. That's the only time it's positive, greater than 0. So that means the domain for this function needs to be negative 2 comma 2. That's what we have. So that's how you find it. It's kind of like you're solving this quadratic inequality. Find the boundaries and find when it's positive and when it's negative, and then pick up the one that really suits for your problem. But just here I'm making it positive because inside ln I should have positive values. The last problem is an application problem. The loudness B of a sound with physical intensity I is given by B equals 10 log I divided by I0. I0 is the physical intensity of a barely audible sound. So it's kind of like in here the decibel value is given in terms of the intensity of the sound and in terms of the intensity of the barely audible sound. So it's kind of like you compare them and then you find the decibel value. So it's kind of like gives you how loud the sound is. I mean, it's really common in like checking this in stadiums and in like concerts and all that kind of stuff. Like you can find apps to measure this. But here it says if a sound has a physical intensity 100 times of the barely audible sound, Can you find its decibel value? It's pretty straightforward because it's given as a quotient of it. Quotient means you're looking at the multiple of that actual value. So b will be, in this case, as you see from here, I is simply 100 times I0. So let's plug that back in here. It's going to be 10 times log I is 100 times I0 divided by I0. So that's what we have. And as you see, here I0s will cancel out and you get log 100. But log 100 is basically 2. Because which power of, and you can use a calculator, but which power of 100 is, but which power of 10, base is 10, which power of 10 is 100 is the second power. So we just get that 2, so it's going to be 10 times 2, which is 20 decibels. So I hope you enjoyed the video. These are some examples about the logarithmic functions. Thanks for watching. Bye.